Welcome to our lesson on continuity in calculus. Today we'll discuss limits and continuity over intervals. Let's start with continuity on open intervals. A function f of x is continuous on an open interval. This is true if three conditions hold. First, f of c is defined for every point c. Second, the limit as x approaches c exists. Finally, the limit equals f of c. This means no breaks, jumps, or holes exist. Now, let's consider an advanced problem. Show that the function f of x equals 1 over x minus 5 is continuous on the open interval from 4 to 5. To check continuity, we pick a point c in the interval. Since c is between 4 and 5, f of c is defined. Next, we verify if the limit exists. The limit L is given by limit as x approaches c of 1 over x minus 5. This simplifies to 1 over c minus 5. As c is less than 5, L is finite. Since the limit equals f of c, the function is continuous. Now, we will explore continuity on closed intervals. A function f of x is continuous on a closed interval. This is true if it is continuous on the open interval. It must also be right continuous at the left endpoint, and left continuous at the right endpoint. Next, let's solve another advanced problem. Determine if the piecewise function f of x is continuous on the closed interval from 0 to 2. The function is defined as x squared for x less than 1. For x equals 1, it equals 2. For x greater than 1, it equals x plus 1. We will check continuity at x equals 1. The limit from the left is limit as x approaches 1 from the left of f of x. This equals limit as x approaches 1 from the left of x squared. Thus, we find it equals 1. Now, the function value at x equals 1 is f of 1. We find f of 1 equals 2. Now, the limit from the right is limit as x approaches 1 from the right of f of x. This equals limit as x approaches 1 from the right of x plus 1. Thus, we find it equals 2, since limit as x approaches 1 from the left does not equal f of 1. The piecewise function is not continuous on the closed interval from 0 to 2. Next, we discuss continuous functions on domains. A continuous function must be defined over its entire domain. Common continuous functions include polynomials and exponential functions. They don't have any discontinuities. Now, let's solve another advanced problem. Consider the function g of x equals sine of x over x for x not equal to 0, and g of 0 equals 1. We need to show that g of x is continuous. For x not equal to 0, g of x is continuous. Now, we check continuity at x equals 0. The limit as x approaches 0 is limit as x approaches 0 of g of x. This equals limit as x approaches 0 of sine of x over x. From the standard limit, we know this equals 1. Since g of 0 equals 1, we have a match. Thus, g of x is continuous on the entire real line. Now, let's move to piecewise functions and continuity. Piecewise functions are continuous only if the pieces connect at endpoints. Each piece must satisfy continuity at junction points. Consider the function f of x equals x squared for x less than 0. And let f of x be ax plus b for 0 less than or equal to x and less than or equal to 1. For x greater than 1, it equals 3. We need to determine a and b. We check continuity at x equals 0 and x equals 1. First, at x equals 0, limit as x approaches 0 from the left is 0 squared. This gives us 0. Now, at x equals 0, f of 0 equals a times 0 plus b. Thus, b equals 0. Now, we move to x equals 1. At x equals 1, limit as x approaches 1 from the left is a times 1 plus 0. This simplifies to a. The function value at x equals 1 is 3. Thus, we set them equal. So, a equals 3. To be continuous, we need a equals 3 and b equals 0. Next, we discuss graph behavior of continuous functions. The graphs of continuous functions can be drawn without lifting a pencil. They take all values between maximum and minimum. Continuous functions appear in many mathematical applications. Now, let's tackle an advanced problem. A function h of x is continuous on the closed interval from 3 to 7, with h of 3 equals 2 and h of 7 equals 5. If h of x is strictly increasing, what are possible values? We can demonstrate this using the intermediate value theorem. The theorem states that for any value k, this is between h of 3 and h of 7. There exists at least one c in the interval. Thus, h of c equals k. Since h is strictly increasing, we see this behavior. Values of h of x will take every number. This happens between 2 and 5. Therefore, possible values for h of x range over 2 and 5. Now, it's time for our final challenge problem. Pause this lecture and try to solve the problem. Determine if the function f of x equals x cubed minus 3x plus 3 for x less than 1, and kx plus 1 for x greater than or equal to 1. Can this function be continuous at x equals 1? Find the value of k. First, we evaluate the left limit at x equals 1. We find this limit equals 1 cubed minus 3 times 1 plus 3. Thus, it simplifies to 1. Now, evaluate the right limit at x equals 1. The function value at x equals 1 is k times 1 plus 1. We have to set them equal for continuity. So, 1 equals k plus 1. Solving gives k equals 0. Therefore, the function is continuous at x equals 1 if k equals 0. Thank you for participating in today's lesson.